Good morning to everyone. Good morning. Okay. So, what we have discussed yesterday? Can anyone? What and all we have discussed? In the last class, what and all we have discussed? So we have discussed about Frankel defect, then Schottky defect, right? So that's what we have discussed in the last class with respect to ionic solids, which will show these two types of defects. Now, can you tell me the difference, or if I tell among these two, in any one case, there will be decrease in the density of the solid. Which is that one? Among these two, in one case, there will be decrease in the density of the solid. Which is that one? Yes, that is with respect to, yes, Archit, that is with respect to Schottky defect, where there will be decrease in the density of the solid. Why? Because there will be vacancy which will be created. There will be creation of vacancy. No, Akash, it's not a dislocation, it is vacancy. Okay, so that's where we have the Schottky defect, which is going to make the density of the solid to get decreased, right? And equal amount of anions and cations will be removed, or it will be vanished that from that particular point. So that's why it is called as vacancy defect. Okay. Now, when it comes to Schottky defect, someone had written dislocation. Yes, Schottky defect can also be called as dislocation. Can also be called as dislocation defect. Now, what will happen to the density in Frankel defect? Whether it will increase or it will decrease. So, what will happen to the density of the solid in Frankel defect? Whether it will decrease or it will increase. Okay, fine. Yes, Archit. There will not be any change with respect to density, because in case of the Frankel defect, as a crystal if I take, so there will be movement of atoms or molecules from one point to the another point. It's not removed, it is moving, right? So it will make in original place vacancy, but in new place it will make interstitial. So therefore it is a dislocation. Yes, Purnima, even you are right. So it will remain same, since there is no removal of any atoms, there is no addition of any atoms. So it will be remaining same. So keep these things in your mind. Now, which type of ionic solid will be showed by Frankel defect? Which type of ionic solids will show the Frankel defect? Fast. So which type of ionic solids which will show the Frankel defect? So it can be silver bromide. Yes, sir. It can be silver bromide or zinc sulfide. Silver halides. In general, we can tell silver halides. Right? So it can be silver chloride, silver iodide, silver bromide. Right? Along with that, we have zinc sulfide. So what I mean to tell here is, wherever there is a large difference in the ionic size, right, those type of elements will show the Frankel defect, right? Now when it comes to Schottky, that's what we have discussed. In case of the Schottky, whatever ions are there, there will be difference in their radius, no doubt, but not much difference as that of the earlier one, right? So that's where we have the Schottky defect, which will be shown by alkali metal. Okay, it will be shown by alkali metal ionic compound, where alkali metals will be in water, which will play as a cations. Okay, so that's where we have the Schottky and Frankel defect. Fine. Now, when I am talking about impurity defect, now you should tell me what do you mean by impurity defect. For example, I have sodium chloride. Which can be mixed with strontium chloride, right? So now what will happen? Now there will be displacement of sodium ion by the another cation, since anions are constant. So there will be displacement of one particular ion cation with the another cation. So that's where it will lead to the impurity, right? Now total charge should be remaining same in an ionic solid. So therefore strontium Sr plus 2 is going to displace 2 sodium ions, right? So that's where, yes sir, that's where we have the impurity defect. But in general we can tell even alloys, they are the example for impurity defect. In case of the semiconductors, they are also can be examples for impurity defect, right? Now then we have discussed about F center. Now you should tell me what you mean by F center. So F center is nothing but free electrons which are present in a, or which is shown by metal excess defect, where if I take sodium chloride crystal, if I heat this sodium chloride in the presence of sodium, now what will happen? So there will be formation of free electrons, or there will be release of free electrons. So they are called as F center, yes, or Farben-Genter center. Okay, so which is nothing but a free electrons present in a crystals due to the metal excess defect. That's why they are called as F center, because they will show the colors. Those crystals which have this defect, they can show the colors, right? That's what we have seen. Sodium chloride yellow color, then lithium chloride pink color, right? Potassium chloride, they will show the lilac or light violet color. So that's what we have discussed. Fine. So that's where we have the F center or Farben-Genter center. Fine. Same way we have another example. We have discussed with the another example, that is zinc oxide. When zinc oxide is heated, it will turn to yellow color. What is the reason? That is once again because of the metal excess defect, where there will be formation of free electrons, which will give the yellow color to the zinc oxide crystal when it is heated up, right? So that's what we have discussed. Fine. Now when it comes to metal deficiency, one of the example we have discussed is iron oxide, which is the best example for metal deficiency defect. Fine. So these are the things which we have discussed in the last class. Now we will come to next point, another property of the solids, that means with respect to the electrical conductivity, right? Now in physics you might have already discussed, we have insulators, right? So which will resist the electric conductivity, right? Then we have non-conductors, then we have the non-conductors, so now semiconductors, then conductors. So non-conductors and insulators, they are overlapping, no doubt. Okay, so there will be no conduction of electric current. So that's where we have the non-conductors. That is done. Now when I am talking about conductors, they are actually involved in the, or they can have the capacity to conduct the electricity. So most of the metallic solids, they have that capacity of conducting the electricity, right? So they are called as conductors. Now we have some of the elements which are called as semiconductors. That means they can conduct the electricity but not efficiently. They can conduct in a mild way. So those type of elements are called as semiconductors. Now these semiconductors can be made a good conductor, or its conductivity can be enhanced by mixing with other elements. By mixing with other elements. That's why I told whatever semiconductors which are present, they can be due to the doping of some of the element with other element. That is process is called as doping, right? Now whatever semiconductors which are present in our mobile phone or computer, so all those semiconductors, they are not in pure form, where there is an impurity defect, where there is a impurity. So we can call it as impurity defect, but which we have done purposefully. Why we have done purposefully? To enhance the conductivity, right? That's where we have the semiconductors. Normally group 14 elements. So normally group 14 elements like silicon and germanium, they have this capacity because of their atomic size. Because of their atomic size, which will make them to behave as semiconductors. Carbon belongs to same group, right? Same family. But carbon cannot behave as a semiconductors because it's a smaller size. It's the first element. So that's why we have the silicon and germanium, which will be acting as a semiconductors. Fine. Now, why we have different varieties of elements based on the conductivity, right? Some of them are non-conductors, some of them are semiconductors, and some of them are conductors. What is the reason? As I was telling in the last class, if you imagine this one as a valence shell, this one as a valence shell, same way here also we have, and same way here also we have. Now, when we are talking about the nucleus, we'll imagine nucleus is somewhere here. Okay? Now we have an electron in the outermost shell. We have the electron. Now when you pass the energy, depending on the nuclear force, some of the electron, they will be jump to higher level. Some of them, they will jump to higher level. Fine. So that's where we have the condition. When you are providing the energy, electron is moving to bit higher level, electron is moving bit to higher level, and electron is moving bit to higher level, no doubt. So based on that, I can tell amount of energy what I have supplied is same for all the three elements. But for first element, electron has moved to this much distance. But for second element, it has moved to bit higher distance. But when it comes to third element, it has moved to very higher level. So that's where we have the nuclear force, which is going to one of the factor, which is going to decide to what level electron can move. To what level electron can move. Fine. That's where electron should be in such a way that where it should be available for the conductivity. That's where it is called as conduction band. That's where it is called as conduction band. Now if you have a substance or element, for example, we will imagine first case, the electron is very close to the outermost shell. Now the problem here is it will come back to the outermost energy level very fast because it is near. Since it is near, it will come back fast. Now it is not much available for the conductivity, right? So in this case, since electron has moved a large distance to move from here to here, then it will take some time, right? and it has moved a large distance. Now it might be available for the conductivity, right? It might be available for the conductivity, but the problem here is that distance. It's of very high distance, right? But when it comes to here, it's of moderate. It's of moderate, where electron has moved from here to here. Now this electron can be available for the conductivity. So what I mean to tell here is, when I am talking about conduction band and outermost energy level, when I am talking about conduction band and outermost energy level, so that's where this one and this one, it will be decided by type of element. Okay? Yes, you are right, Amit. So which will be majorly due to the nuclear force. So this will be decided by majorly by the type of element. Fine? If that gap is too high, then they cannot act as a good conductors, because electron is moving not to the conduction band, it is of large distance, right? So therefore those elements where conduction band and outermost energy level distance is bit close, where electron can easily achieving, if the electron can move to that particular energy level, then they are called as good conductors. Okay, but it should not be too close also. So same way, when I am talking about semiconductors, there is a medium distance. When I am talking about semiconductors, there will be a medium distance between outermost energy and the conduction band. So what do you mean by conduction band? Conduction band means where if you supply the energy, so electron which is in the higher level, if it is available for the conductivity, then it is called as conduction band. Okay? Otherwise what will happen? Immediately it will come back to the ground state, no doubt. Immediately it will come back to the ground state. So therefore, depending on the level of difference between outermost energy level and the conduction band, so property of the material, that is conductivity property of the material will be varied. Now when I am talking about selenium and germanium and all, which are called as semiconductors, that's where the distance between outermost energy level and the conduction band is of moderate compared to iron rod or any other good conductors of electricity. It will be of medium distance. All of you have understood? So that's where we have the semiconductors. Fine? So when I am talking about semiconductors, say for example, for electronic goods, I cannot use the iron rod. So in conduct pass, electricity pass ಮಾಡಬೇಕು ತಾನೆ, there should be charge, movement of charge. So we will make iron. The problem with this iron and all is they can be easily rustable. It can be rusted. That is one thing. And conductivity will be too high also. Heat generation can happen. So to avoid all these things, they will go with the semiconductors. There should be conduction, but along the same time, there should not be any other side problems. Okay, na? So that's why they are going with the semiconductors. But only thing here is, if you use a pure form of semiconductors, it's of no use. Okay? So simple ಆಗಿ ಸುಮ್ಮನೆ ನಿಮ್ಗೆ ಅರ್ಥ ಆಗಲಿ ಹೇಳಬೇಕು ಅಂದರೆ, I may not be 100% correct also, because I don't know much about electronics. For example, if I take a pure semiconductors, okay, so if I am keeping it for a mobile phone, message will be transmitted, everything is happening, right, which will happen in fraction of second, it may happen in few minutes. You have given some instruction, okay, you have typed some instruction, but to see the result, it may take 2 minutes, 3 minutes, because that transmission is getting delayed, right? So same logic is applicable. So to avoid that, they will be using, or they will be adding some impurity to enhance the conductivity, to reduce the duration. But at the same time, we should take care that it should not be generating such a high amount of heat also, right? So that's where we have the semiconductors. Now we have one of the word called as doping. So doping is a process. Doping is a process where other element will be added to some other element, like to make the impurity, where there will be addition of one group element to another group element. In this case, since we are talking about semiconductors, so doping is a process where group 14 elements like silicon and germanium will be added with either group 13 or group 15 elements. That is called as doping. Okay. So what is the end result of doping? End result of doping is definitely it will lead to the impurity defect. It will lead to the impurity defect, no doubt. That is the end result. But what is the application? Application here is, due to the doping we are enhancing the conductivity of a semiconductors. We are enhancing the conductivity of a semiconductors. That is the major application. End result is impurity, fine. But application is, it is enhancing the conductivity. That's where we have the doping process. Okay? So when I am talking about group 14, as I told, silicon and germanium, and all of us we know, when I am talking about carbon, catenation property is highest with respect to carbon, where one carbon can bond with another carbon, and the number of carbon, it can go to any length. That is where it is called as catenation. Carbon is dominating. Once carbon is done, next comes the silicon, germanium and all, which are also having catenation property. Right? Now, I will be talking about, first we will go with the P type. Okay, first we will go with the P type of semiconductors. Okay? Now we have the P type of semiconductors. In physics also they will ask, in chemistry also they will ask. So it is bit important. Okay? So now when I am talking about P type of semiconductors, see, this is a silicon which is in interaction. This is not lone pair of electron, it is ion. Okay, I will make it clear. This is ion. Okay? Now this silicon, where they are interacting with each other, interacting with each other. That's why I told catenation property, where silicon is interacting with each other, right? So that's where we have the silicon. So when I am talking about two electron means what? There is a interaction, there is a bond which is present. There is a bond which is happening here. Okay, so Archit, since I am talking about P type, so we can go with group 13. Okay, so group 13. Now this silicon, it will be treated with group 13 elements like boron or aluminum. Normally they will go with boron or aluminum, not both at once, either boron or aluminum, any one of these two. They are going to dope silicon with boron or aluminum. So what is the total valence electron in boron? Yes, sir, check. That group 15 meant for N type. Okay. So when I am talking about boron or aluminum, which belongs to group 13, what is the valence electron in those elements? Here we have 4. 1, 2, 3, 4. 1, 2, 3, 4. Because it belongs to group 14. Right? So therefore, when I am talking about group 13, they should have the 3 valence electron. They should have the 3 valence electron. Yes, sir. They should have the 3 valence electron. Fine. So that's where we have the doping. We are adding or making impurity, where silicon crystal is mixed with group 13 elements. Mixed with group 13 elements. Now what will happen? Some of the silicon will be replaced by the boron or aluminium. That's what it will happen. We have the silicon. Okay. So here also we have the silicon. Okay, here I will make it as aluminium. So here we have the aluminium. Okay. Silicon. So fine. What is happening here? I have shown 3 layers. Silicon. So that's what we can see. There is a impurity which has been found. Here only silicon were there. But here one of the silicon I have shown, one of the silicon has been replaced by aluminium. Now the problem here is there is a shortage of electron to share with this silicon. There is a shortage because aluminium does not have the valence electron which can make the bonding with this silicon also. Maximum aluminium can go with 3, not more than that. So that's where there is a shortage, right? There is a lack of electron. There is a lack of electron, right? So therefore, due to the lack of electron, we will call it as a positive hole. We will call it as it's not a charge on aluminium, please. Don't get confused. I am not talking about the charge on aluminium. No. Aluminium does not have any charge. Since there is a lack of electron, we will call it as a positive hole. We will call it as a positive hole. Okay? Where there is a lack of or shortage of electron. This silicon is upset. Oh my God, I have one extra electron. I cannot make the bonding. I want electron. I want electron, it will be telling. Which one? This silicon. Aluminium is happy because it is saturated. But what about silicon? It is very, very unhappy because it is left over with lone electron. It wants to make the bonding. So during that time, what it will do is, it will drag the electron of neighboring element. It will try to take the electron of neighboring element. So due to that, movement of electron. Now what will happen? There will be formation of positive hole here and this will be vanished. Whether I am clear? So now due to the movement of electron, there will be a positive hole which will be now nullified, but positive hole will be formed here. So like this, the movement of electron will take place. Observe it carefully. In this direction, electrons are moving. All of you will agree? As I have shown the arrow, in this direction, electrons are moving. But if you observe it carefully, in opposite direction, positive holes will be moving. In opposite direction, positive holes will be moving. All of you will agree? So that's what it will happen. Since electron has moved here, this positive hole is nullified, but there is a formation of positive hole here. Now due to that, electron will move here. This positive hole will be nullified. Now positive hole will be formed here. So what I mean to tell here is, positive hole is getting shifted from left to rightward direction, and the same time since electrons are shifting from right to leftward direction. Fine? So this is how, when you connect it to anode and cathode, this is how the movement will take place. Actually there is a movement of electron. Positive hole is not moving. Due to the movement of electron, it looks like even positive hole is getting moved. Fine? All of you will agree? So that's how P type of semiconductor is going to function. Right? Since there is a movement of electron, which we cannot observe actually because there is no negative charge which will be created due to the movement of electron. But still, since there is a movement of electron, it looks like there is a movement of positive hole. There is a movement of positive hole, like resonance in benzene. Okay, Purnima, when it comes to resonance, there is no question of positive. Okay, that will be equally distributed. Oh, you mean to tell there is a moment of positive hole. That we can consider, but here there is no pi electrons. Here there is no pi electrons. That is the major difference. In resonance and all, there should be presence of pi electron. But you can tell that, okay, fine, there is a moment of charge from one side to other side. That is fine. But in reality, there is no pi electron. We cannot call it as resonance exactly. Okay? So in that way, since there is a moment of positive charge, they are called as P type of semiconductors. Right? If there is no hole, what would have happened? There is no conduction because all are saturated. No free electrons. Since there is a doping, now there is a conduction. Fine. So that's where we have the P type of semiconductors. Very important one here is P type of semiconductors will be formed when group 14 elements. Here I have taken silicon, even germanium also you can write. So that's where we have the P type of semiconductors which will be formed whenever group 14 element like silicon is doped with group 13 element like boron and aluminum. Anyone? All of you have understood? So why they are called as P type? Because there is a moment of positive hole. So therefore they will call it as a P type of semiconductors. All of you will agree? So we'll move to the next one. Okay, fine. So now we will move to the next one, that is N type. Don't use capital. So N type of semiconductors. We'll move to the N type of semiconductors. Now, when it comes to N type of semiconductors, we are going to mix here on the atom, right? We are going to mix group 14 elements. I have kept silicon once again. We are going to mix group 14 elements with group 15. That time only Archit had written. So we are going to mix with. Sir, I have doubt. Sir, it is related to. Can we have a discussion afterwards, Archit? I think today we can finish it fast. Then we can have a discussion. Fine? Okay. So now, when I am talking about group 15, because after this I have magnetic property, then today's class will be done. Okay? Then we have group 15 elements. So group 15 element means it can be either phosphorus or it can be arsenic. Anyone. Either phosphorus or arsenic. Okay? So now, group 15 elements, when it is added to silicon or germanium, that is group 14. So total valence electron is 4. So total valence electron is 5. Now when I will be mixing, there will be formation of or displacement of one of the silicon by the phosphorus. Now what is happening? Phosphorus is having extra electron. Extra 1 electron is left over. So 1, 2, 3, 4. 4 is involved in bond formation. But there is 1 extra electron which is present or which is left over with phosphorus because silicon, it cannot make bond with the phosphorus because 4 is already done. Right? So yes, Archit, that's where we have the electron rich condition. In earlier case, P type, electron deficient. But here, in N type, electron rich. That's where N negative, in P positive. So negative because electron rich. So which electrode is present on which side? Now there will be movement of the electron. So for example, if I have cathode and if I have anode, okay, I should have taken anode here. Now the movement of electron, since anode is on the left hand side, electron will be moving here. If you have taken anode there, electron will be moving that side. That's where we have the semiconductors. As a silicon in a solid, they will be poor conductors, but since there is an addition of phosphorus or arsenic, Due to the excess electron, now they will be behaving as a good conductors. So that's where the impact of the doping. This is nothing but n type of semiconductors. All of you have understood? So one of the application, if I want to explain, anyway, in detail I will not go. All these things you will be discussing in your physics, that is related to transistors and all, you will be discussing that. Diodes, right? So I am not going to discuss, I am not expert in those. But to be simple example, if I want to give, if I want to talk about solar panel or solar cell, okay, now which will be utilized for heating purpose, heating the water or electricity and all, right? Now what they will be doing here is, they will have the two layers, silicon only, two layers will be there. So upper layer, it will be N type. Upper layer will be N type. Why N type? Because here silicon is mixed with the phosphorus. We'll imagine phosphorus. Now lower one will be P type. Lower one will be P type, where silicon is mixed with the aluminum.